Hi, welcome. This is an overview video of the process or the concept of a process. All right, so a process, when you have a process, you actually have a set of actions that are done to produce a desired result, right? So everything that runs on your computer is your operating system needs to manage all of these tasks that are on your computer. And so the definition of a program that's active is called a process. Some things that are associated with a process would be a PCB. It's not always called a PCB, but that stands for process control block. And some different operating systems have different names for this, but this is essentially the data structure that the operating system will create that has all of the information about every active process on your system, because your operating system makes it seem like things are all executing at the same time, but as it switches, it needs to save information about each process and then load the information about the next process. That's called a context switch. I mean, think about it. You don't want to restart a process at the beginning. If you're doing some actions and then maybe you're going to switch and use the processor for something else, you want to save the current state of the active process and load the state of the next process. And each active process will be in a particular state while it's active on your system. So different operating systems have different names for different states, but we're just going to cover the general states that a process could be in. All right, so a process is an active program. So actually a program is just inactive. It's just a set of instructions, because you've written programs, you have your code, and then you have any other files or data that's associated or needed by your program, but as it sits there on the disk not doing anything, it's inactive. Once you initiate it, either by a command line or clicking on it, or somehow you turn it from an inactive entity, like a set of code, to an active entity, then it becomes a process. So this is actually the things that I just said. We have to keep track of the current activity, the program counter, all of the information, everything where the process was located. And if you're going to switch from one process to another, that's called a context switch. You have your stack, which has your temporary data. And when you have all of your functions, you have your parameters, all of your local variables and all of that. And then you have any extra global variables, your data section, and then any dynamically allocated memory during execution would be stored on the heap. So again, a program is passive, a process is active. It becomes active when it's loaded into memory. The process control block, or it could be a different name, but each operating system will create for each process a data structure. And for our purposes, we will call it a process control block. So one program can be several processes, and I'm sure you know that. You can launch, just say for example, Microsoft Word. You can launch Microsoft Word, and then you can launch a separate instance of Microsoft Word, and those would be two active processes that are the same program, but they're different, right? One Word is doing one thing. I know you can have multiple documents, but if you relaunch Microsoft Word separately or Excel separately, you are launching two active processes of the same program. All right, so what kind of information would be in the process control block? Well, you have the state of the process, which we will go over in a moment, what the current states are. Again, different operating systems have different names and lists for the states, but we will go over the general states. You will have a case studies to work on in which you will go into more details on specific operating systems for different features that we will be discussing and concepts throughout this course. There's a program counter. That's the location of the next instruction. Like I said before, you don't want to restart each process every time you switch from one job to a next. You don't want to have to restart it every time. The CPU registers, CPU scheduling information. We will be talking about different types of CPU schedulers. So this will have to be, certain processes will have different types of scheduling algorithms. Different operating systems will use different types of scheduling algorithms, and this type of information would be in the data structure that defines each active process. Memory management, you want to know what memory has been allocated to the process. Accounting information like time used and time limits and how much it's been on the CPU, stuff like that, and the status of any devices that are or open files that are associated with the active process. This is just a general overview. Again, for specific tasks, there might be some additional information that needs to be kept in the process control block. The process control block is a data structure that each operating system keeps for each active process in your system, so it can keep track of all of the active processes. So let's talk about the states. The first state is when it goes from being an inactive entity to an active entity, and then it would be in the new state. It's created. Then sometimes it's created and then it needs to be loaded into memory, and that means it's ready for the processor. So the next place it would be is in the ready state. Running. The running state means that it is currently using the CPU and executing instructions. Waiting. Processes are waiting all the time. Sometimes they're waiting for the results of another process. Sometimes they're waiting for data from a file. So while it's waiting, another process could be on the CPU running. So it's still active. It's just waiting for an event. It's not ready because it's waiting for an event. So keep in mind, new means it was created, but it still needs to be loaded into memory. Ready means it's waiting. It is waiting, but it's waiting for a different reason. It's actually ready to go, but it's waiting for the processor to, maybe the processor is a separate process is currently using the processor. Running is when its instructions are being executed, and then the waiting state, so ready means it's ready to go, but it's not on the processor. Waiting means it's not ready to go, it's waiting for some event to occur. And of course, when it's done. Now there's different types of terminated as well. So again, when you do your case study, and you will see that there are different ways that the operating systems handle processes when they have finished execution. So here's a diagram of this. So a process could be new. Once it's new, it gets admitted into the system. So the transition should be labeled as well. It's ready. This means it's ready, sitting there. And when it is ready, it is accumulating what's called waiting time. It's accumulating waiting time because it's waiting for the processor. So it's actually ready to go, but some other process is using the processor. Then it gets dispatched and it's running. Then when it's done running, it will exit and be terminated. So here's the thing, this is what processes do, but think about it. They don't just get admitted, wait, do a little thing on the CPU, and then exit. Processes do a little thing on the CPU, then they wait for I/O, or the operating system switches between different processes. So this state diagram right here is just going from if it did one little CPU burst, but actually it could be on the CPU and then it has to wait for an event. So this is the waiting state that I said before, but not to confuse waiting for the CPU and waiting for an event. So there are two kinds of wait. There's wait for the CPU, and then there's waiting for an event, maybe I/O or something, and this could also be called blocked Blocked is usually when it's waiting for a different process, but I just don't want to confuse the concept, the different terms of waiting, because processes waiting here are ready to go. Processes waiting here are not ready to go. So once they become finished, the event is completed, then they have to move back into a state in which they are ready. So they do not accumulate wait time here. They accumulate wait time only when they're ready to go. And then sometimes a process could be on the processor and for some reason it will get interrupt. Maybe there's using an algorithm with time slices, so it gets interrupted for a time slice, or maybe it gets interrupted because a higher priority process comes along. We will be discussing all of these when we get to CPU scheduling. All right, so that's an overview of processes. There are more videos that go in more detail, so be sure to watch them and read the notes and do the exercises and everything. And now we're just going to talk a little bit about the different system schedulers. So in your system, you have a set of queues, and this is not all of the queues, but this is just an overview of some of the queues. So you have the first queue here would be the job queue. So that would be the set of all processes that are in the system. That means all the processes that are ready to go, but they might not be in the ready queue. They are active. So this is all of the programs that have become active processes. The next one is the ready queue. This would be set of all the processes that are actually in the ready state and accumulating wait time because the processor is busy doing something else. And then you have queues for your devices. So the idea is that you want to keep the CPU busy all the time, and we're going to do some studies on CPU scheduling algorithms and different sets of data to see which different types of algorithms work with different types of processes. In your system, you have 3 different types of schedulers. The first one is the long-term scheduler or the job scheduler. And this is going to select, if you go from here and a process is new, it needs to be admitted into the system and put into the ready queue. So that's the job of the long-term scheduler. As soon as a process gets admitted into the system, as soon as a process gets active in the system, this unit of your operating system is going to admit it. Maybe it can't be admitted. Maybe you have too many active processes. Maybe it's going to have, processes are going to have to wait. This does not work very often because usually, nowadays we have so much RAM that there's usually space, but this long-term scheduler needs to kick in because in order for a process to be ready, it needs to be loaded into memory. So this long-term scheduler is going to have to kick in and activate the memory manager to help locate and allocate memory for a process that has been for a program that has become a process and needs to be admitted into the system. Then you have your CPU scheduler. This is where we have our different algorithms. So the CPU scheduler works all the time because you have a list of processes that are ready to execute, and there are different algorithms that can be used to decide which one is going to get the CPU next. So of those that are in the ready queue, that's the CPU scheduler, you're going to have to decide which one is going to get dispatched onto the CPU and go into the running or executing state. And there are different algorithms and different ways that decisions are made. Obviously, the most simple way is the first in, first come, first serve. And many systems only have a short-term scheduler. They don't have a unit that just if a process comes in and memory is full, then they can't get admitted to the system until things get freed up. Some systems incorporate another schedule, which is called a medium-term scheduler in some textbooks, which is called swapping. So sometimes when you fill up memory and then new processes get admitted into the system, there's not space for them. So maybe there have been some inactive processes that can be swapped out onto your hard disk and allow for the new tasks to be brought in for different reasons. So it can be added. It is not all systems have it, and this is really an overview of the ways that processes get introduced into your system. Okay, so let's just go over a couple more things about processes. Some processes are more IO bound. What does that mean? It means that they do very short CPU bursts and spend less time on the processor and more time waiting for events. Or you can have CPU bound processors, and these spend more time doing computation and have very few but long CPU bursts. So an IO bound process has short CPU bursts, and a CPU bound process would have longer CPU bursts. So if you're running all of your longer CPU bursts, then your shorter CPU burst processes might have to wait a long time. Sometimes your operating system will use techniques to put some of the shorter ones in there. Now, another thing to keep in mind is that you don't really know how long a CPU burst is. Like a process doesn't have a thing in its PCB that indicates that it is a process with shorter bursts. So sometimes there are different ways to deal with this. Maybe processes that tend to be have shorter CPU bursts might have higher priorities or different priority numbers. A priority number could be something that is added to the PCB. We also have already talked about the degree of multi-programming. So this is not multi-programming, and multiprocessor are not the same thing. Multiprocessor just means more than one processor, more than one CPU. Multi-programming just means the number and the type of active programs in your system. So the degree of multi-programming is just a measure of how many processes or programs are active at any given time in your system and what type of processes they are, and this is all managed by your operating system. I already went over the context switch, but we will talk about it again. Each process has a context. The context of each active process is located in the process control block, or PCB. When the CPU is switched from one process to another, the operating system needs to save the state of the old process and load the save state from the new process. So each time you make a switch from one process to another, you do what's called a context switch. The thing about it is the operating system needs to use the resources of the system in order to perform a context switch, so a context switch is overhead. We talked about what overhead is. That overhead means that the operating system needs to use the resources of the computer system to do the management work. So when this is being done, the your actual tasks that you want to perform on your computer are not actually getting done. So obviously you want to minimize the overhead, and more context switches means more overhead. So one more thing about limited direct execution. So sometimes you can run user programs directly on the CPU, but of course the operating system is the manager and the operating system needs to take control. There might have to be some system calls for system tasks. So this becomes a very complicated process because even if you want to run user programs directly without always going through operating system, you want to maintain security and you want to keep processes away from each other. So there's still a lot of management and overhead involved in even doing limited directed execution. So what you do here is just like you can virtualize memory, you can virtualize the CPU. You can share the CPU with jobs, and it seems like things are running at the same time. You run one and then you switch. You are time sharing the CPU, kind of the same way that you are presenting the CPU, you're making it seem like things are all running at the same time, but you're actually switching. So you still have to do context switches. Of course, you would have dual mode operation because there are things that must be done only in the kernel or system mode, and that cannot be done in user mode. There are, privileged instructions that you can't allow user programs to access files or memory or some of these things that the kernel must take control over. And that's done through systems calls. And when the user process is executing instructions, if something becomes a restricted access or that needs the operating system involvement, then there's a trap and there's a list of system calls, and then the operating system will take over. And many systems use this concept of dual mode operation, so they change the user process from executing in user mode into kernel mode to perform those instructions. All right, processes communicate. They need to communicate with each other. Many times if they are threads of the same process, so you do have the idea that you can have one process like this that has different threads of execution. So if that's the case, then they share memory, they share resources, they just have their own unique identifier, and there are different techniques on how threads work. Shared memory threads can cause some concurrency issues, and we will get into that when we get to the concurrency section of this course. But there are basically two types of processes. So if you have threads would be cooperating because they work together in the same process. And most of the time that's the point, is that it's to speed up execution. But if you have two separate processes here, and each of these just have a single thread of execution, sometimes processes can be independent, which means this process does its own work and this process does its own work, and they never have to deal with each other, so they're independent. If you have independent processes, you're not going to have any issues with concurrency, and also they don't have to communicate. But many times you have this process which is doing something, and then this process needs to wait for the result from that process, or vice versa, or for some reason they need to communicate, they need to share data, for whatever reason, and those would be considered cooperating processes. When you have cooperating processes, there are things that need to be taken into consideration. Obviously concurrency, how deadlocks, how to control the order in which things happen, and make sure that you're always getting the current information, reading and writing, and some of those problems which we will discuss in the concurrency section. But even before we discuss that, we want to understand that they need to communicate, right? So if this process needs to send data to that process, and this process needs to receive that data, there are different ways to communicate. They could either set up a communication link for synchronous communication, or they could do asynchronous communication where one process just sends a message and then the other one just gets it whenever, but it doesn't stop. Synchronous would mean I'm executing like this and I send a message over to this process and I need to stop everything I'm doing until I make sure that this process receives my message. Asynchronous would be I'm executing, I send something over here and I just keep on going, and at some point I will find out. So there's different reasons for this. This is a asynchronous online course, meaning I am recording these things, I'm posting things, and you guys are working at a different time than I am. But sometimes you have synchronous online courses where you actually meet at a specific time. So that's the concept of synchronous and asynchronous. This part right here, we're just talking about the concept, not any specific reasons why you would need this, but we will, obviously get into more details. This is an overview video. So if you do have cooperating processes, they need to communicate. There are two ways in which they can communicate. So reasons to communicate, obviously, share information, speed up, more modular, convenience. All right, so there's two ways in which they communicate. The first way is by sharing memory. So threads of the same process share memory. Most of the time, processes do not share memory because that's one of the reasons that that's one of the reasons that the operating system gets involved is to keep processes, those are privileged instructions to access the memory of another process. So if processes were to share memory, that needs to be set up. I know that sometimes you can embed in Microsoft Office processes, you can embed spreadsheets into like Word, for example. So if you're running Word and it's got an embedded spreadsheet and you're editing in Word, then these would be sharing memory because you're making the edits directly in both Word and Excel. But most processes, most of the time, the idea is to keep processes, from accessing the memory space of another process. And in that case, you would have to do some type of message passing. So again, another way to get over the issues of, the time it takes to send messages is the thread technique. So threads do share memory, and sometimes processes share memory because there's a lot of overhead in sending and receiving messages, and there are different ways that messages are sent and received, and the operating system needs to be involved because most of the time these communication links need to be set up and involve the operating system. All right, so this is an overview on processes and the process concept.